My recording.
Yes, ma'am.
Okay. Hope you're able to see my screen.
Yes, ma'am.
Okay.
Yes.
Yeah, okay. I welcome you for the uh, week 12 live interactive session for the course Polymers, Concepts, Properties, Uses and Sustainability. As usual, we'll have a brief recap of lectures of week 12. So, lectures of week 12 were on polymers and environment. Okay. So, lecture 84 is on microplastics, aerosols, and sediments. Basically, the sustainability aspect and the environment aspect of polymers. So here, the lecture started with what is the freight and transport. There was a earlier discussion also on freight and transport of polymers, right? They have very low density similar to that of water, and they have a long life longevity, right? That it cannot be degraded, which are really concerns in terms of sustainability point of view. So how are these released in the environment? So they are of different sizes also. You will have macroplastics, microplastics, mesoplastics, and nanoplastics. And what are the origins? They may be of a primary origin directly, or some secondary kind of origin also. Okay. So and then for example, a direct effluent from a factory can be a primary origin, and secondary origin, it can be broken down to some other sizes, and then it meets with the environment phase, like your soil, land, or water. Okay. And then there was a discussion on microplastics. So what are microplastics? Okay, what is the size range of a microplastic? Okay, they generally come in the size range of some 5 microns to less than 1 mm. Okay, this is the broad size range of microplastics. Okay, and what is their surface to volume ratio? How are the interactions with the surroundings, and how much they are prevalent? So they are present in terrestrial environment, okay, in land, water, and soil, and also sometimes even in organisms, due to bioaccumulation, these microplastics, they get into the digestive tracts of animals, flora, sorry, fauna also, like marine environment, or even terrestrial environment. Okay, they are present in air also because of their size. I just mentioned, right, it is of micron size. So because of their fine sizes, and as we know that they are low dense materials, so they have the capability of mixing with air even. Okay, so how much is their prevalence, and in what form they are all prevalent? So these were all discussed in this lecture. Okay, the next lecture was on biodegradation of polymers. This is again on sustainability aspects. Okay, so here, what are the type of degradation of polymers in environment? For example, there can be a UV degradation, okay, or thermal based degradation, mechanical degradation. Okay, so these kind of degradation can happen. And another, a very sustainable aspect of degradation of polymers is biodegradation. And next is the sedimentation transformation. So, a classic example of sedimentation transformation is your fossil fuels, right? Because of sedimentation in the, it has been buried in the soil long time back. They got converted into fossil fuels. So, this kind of transformation can also happen in case of polymers. Okay, and then there was a detailed discussion on biodegradation of polymers. Okay, so what are the factors involved in biodegradation? Okay, what are the different parameters involved, and what are the conditions, like for biodegradation? Your pH will be important, presence of water or moisture, because these are biodegradation means there is a role of microorganism that is happening, right? So microorganisms lead some pH, It needs certain amount of moisture or water for the survival. And the amount of oxygen required will differ from an organism to another organism. For example, in certain cases the biodegradation can be aerobic, that is it happens in presence of oxygen. In certain cases it can be anaerobic, that is it doesn't require any presence of oxygen. And then your salt, ionic strength, so all these parameters play a role in biodegradation. And similarly, it's not only the environment condition that plays an important role, but the structure of polymer itself. Okay, what is the molecular weight? Okay, and the length of the polymer chain. Okay, if it is a very high molar mass polymer, then the extent of biodegradation will not be that much. Okay, it may have some difficulty because the big molecule has to be broken down, and then it should be used in the bioprocess of the microorganism. So if it's a very large molecule, it might be difficult. Okay, so it depends on the molecular weight and whether the system is cross linked or not. Okay, and what is the porosity in the material. So because these pores and all, no, they act as a place where the microorganisms can sit when they start acting. And what is the diffusivity? Okay, so that the microorganism is able to diffuse in the polymer. So these all these aspects play a vital role. Okay, and there are aspects like what is the rate of biodegradation, how fast it is being broken down by biodegradation by the microorganism. So if it is going to take hundreds of years, it's not going to really help. Okay, so if the process is quicker, then it is good. Okay, so these aspects were discussed. And then next there was a discussion on biodegradable polymers. So in this part, a kind of refreshing of the old chapters where different biodegradable polymers were discussed. Right, in previous lot of chapters there were discussions, lectures, there were discussion on biodegradable polymers like polylactic acid. There was a discussion, and there was a discussion on casein. Do you remember in previous lectures, set of lectures, in different lectures, one or the other biodegradable polymer was discussed. In one lecture there was a discussion on casein, and in another lecture there was a discussion on hierarchical structure of your collagen, and pectin was discussed, starch was discussed, polylactic acid was discussed, and your polyesters, biodegradable polyesters were discussed. So those gist was given yeah, in biodegradable polymers. Next, the waste management in case of biodegradable polymers. Okay, so again, there was a discussion that the rate of biodegradation is very important. Okay, because it should not be too slow. Also, it should be some optimum, value. And then what is the recyclability of a biodegradable polymer. And for example, in one of the lectures, there was discussion on blends of starch with other materials and all non-degradable, like with polyethylene and all. So polyethylene can be recycled, but when it is mixed with the blended with a biodegradable polymer, the extent of recyclability reduces. Okay, so whether it is it the right choice. Okay, so these aspects were all discussed in biodegradable polymers and polymeric waste management. The next lecture was on biodegradable polymers 1. This was again on sustainability. So, what are different types of polymers with biological relevance? So, this was discussed. So, there are biopolymers. Can you name a biopolymer? What is a
Yeah, ma'am.
biopolymer?
Uh, Found in organisms, polymers found in organisms.
Okay, yes. So, can you name an example?
Protein.
Yes, yes, very good. So, which are, based out of plants or animals or microorganisms. For example, as you said, proteins, and then, pectin, it is from plants. Cellulose is from plants. Collagen is from animal source. So, these are all biopolymers. There is also a category called bio-based polymers. Okay, what is bio-based is that their origin, in the sense the raw materials basically are of biological origin. Okay, so in this itself, there are two different categories. See, one can be bio-based, can be a polymer. You can, have a renewable source from which polymer can be, made. Unlike using fossil fuels and all, or petroleum based, you can manufacture it from a renewable source. But it need not be, necessarily biodegradable. For example, you would have heard biopet, biopolyethylene and all. Okay, here the source of the raw materials are from natural renewable sources, but it does not mean that polyethylene or biopolyethylene and all, it will be biodegradable. Okay, it can be of that type also, or bio-based and biodegradable also, they can be category. Okay, so these were all discussed. Okay, and then what are the degradation claims? When you say a particular material is biodegradable, particular polymer is biodegradable, uh, you know there are certain criteria that it has to fulfill. You cannot say a material partially biodegradable, or over the time it may biodegrade and all. You cannot give as a biodegradable, or it is getting actually degraded by light, like UV radiation, or something, or thermal degradation and all as biodegradation. So there are certain criterias. So what are those which are acceptable, which are the claims that are acceptable as biodegradation, and which are not acceptable as biodegradation? So these were all discussed. Then there was a small discussion on composting. Okay, then there was a discussion on biodegradation of different polymers like polyhydroxybutyrate. So how does it get biodegraded? What kind of enzymes are playing a role in biodegradation of polyhydroxybutyrate? These are generally polyhydroxyalkanoates. Okay, so that was discussed. And then what is the duration? For example, in particular environment, in marine environment, what is the duration of its biodegradation? Okay, in anaerobic condition, what is the duration? In aerobic condition, what is the duration? And what are the steps involved in biodegradation? So these were discussed for polyhydroxybutyrate and polylactic acid. Okay, then there was a brief discussion on starch-based polymeric systems. So starch, what is the composition of starch? Okay, and how much is the crystallinity in case of a starch molecule, starch. Okay, and then what are the different, so starch can be blended with some other material, and you can get up a bioplastic of starch combination, starch with some other material like starch with LDPE or something. And also what you can do is that you can also uh, you know uh, next derive some monomers or intermediate products from starch, and then you can further polymerize it. So in this way also starch can be used. And how can you improve the properties of starch? By adding some plasticizer, and also you may need some antimicrobial agents, because starch, it can be degraded by microorganisms. So during the shelf life it should not be degraded, right? During its service life, starch should not be degraded. So some antimicrobial agents can be added, and to improve properties, certain other materials it can be combined with. For example, it can be combined with the polylactic acid, or it can be combined with some other proteins or something, so that you get a better betterment in properties. These aspects were discussed in this lecture. The final lecture of the week and of the course is biodegradable polymers 2. This is a uses based lecture. Okay, so here application and processing. So the aspects of cost. Okay, cost efficient it should be. So you cannot, it's not only about the biodegradation, you have to also think of cost also, right? In order to make it widespread use of biodegradable polymers. Paul, are you there?
Yes, ma'am, I'm here.
Okay, okay, you're able to follow, right?
Ma'am, I had gone through. I'll go through
Okay.
after the session.
Okay, okay, okay. But you can at least, get some points. Okay. So, in biodegradable polymers too, this is uses based lecture. So, application and processing. So it should be cost effective, right? Using biodegradable polymers, right? Or natural polymers and all, it should be cost effective. Because now polymers are used, all these synthetic polymers are used widespread because of their you know ease of processing, and because of their cost effectiveness. So a similar cost effectiveness should be brought in biodegradable polymers as well. Then only uh, so it's the use of it starts improving, like people will start making biodegradable polymers. Okay. uh, Widespread use will start improving, because commercial aspects, people have to make money also, right? So people will be thinking in that aspect. So there should be some cost effectiveness. So how to bring the cost effectiveness, for example, giving some incentives. Government gives some incentives, like if you're using some biodegradable polymers, you will have certain incentives. For example, that particular factory setup, you need not pay certain sort of taxes, and also those kind of exemptions. So these are all, they are kind of encouraging, so those kind of things. And also, processing also, there should be ease of processing. For example, your thermoplastics, they can be extruded, right? And then you can they can be coated, right? So these kind of processing, the similar process should be used. Okay. So for the biodegradable polymers also, for example, if it is not, you have to use a completely different processing setup for biodegradable polymers, and biopolymers means it's difficult to start up. But if you can just use the similar processing, then to start will be easy, because you have the setup. Only thing is that instead of a synthetic polymer, you're going to use a polymer B, which is biodegradable. So that kind of processing techniques should be developed. Okay, so these aspects were discussed. And what are the most promising application, for example, in case of starch? Okay, so you have to see what are the some kind of difficulties in using starch uh, extensively, that was also discussed. And then what are the promising application? For example, it can be used in agricultural application, as mulch films. They help in retaining moisture in the land. So it helps in better crop production. And then it can be used in some for example, your bone cement. So that kind of an application it can be used. So automotive parts can be made yeah, using starch. So these were all discussed. And similarly, uh, what are the difficulties or challenges in using polyhydroxybutates or polyhydroxyalkanoates? For example, uh, do you know what is the source of this polyhydroxybutyrate? How is it synthesized?
Ma'am, from bacteria.
Yes, perfect. So these are synthesized from bacteria. So if you just look into the output of these polyhydroxybutyrate by microorganism, no, the output will be very less. Okay. So that means for producing a larger quantity, the cost of production will be very high. So that is one of the challenges. So how to work on that, so that that aspect is handled. So these kind of thoughts should be coming in. So currently there is not much of commercial products that are used, but still, you know there are researches that are going on for using polyhydroxybutirates as oxygen barrier, and then as packaging. So these were all discussed. And similarly, on polylactic acid, what are the challenges involved in polylactic acid? Okay, and where is it used for? For example, it is used in your diapers, and then your tissue papers. Okay, cleansing towels. Okay, these are some of the applications where they are used as fibers, non-woven fibers. Okay, fabrics and all. Okay, uh, so these were all discussed. Next, there was a discussion on biodegradable polyesters. Okay, so there was a discussion on polybutylene succinate. Okay, which is a polyester from succinic acid and butanediol. And similarly, there was a discussion on polybutylene adipate terephthalate (PBAT), which is actually a copolymer of a aliphatic polyester and an aromatic polyester. So, what are their properties? Okay. So what is the TG of PBS, and what is the melting temperature? So these aspects were all discussed, and where is it used? For example, they are they can be thermoformed. Okay, that is stamping operation can be done in case of a polybutylene succinate. So that is one of the way it can be manufactured uh, for commercial products. Okay, thermoforming, where stamping operation, thermoforming, can you say an example in which product your thermoforming is used? This was discussed in your polymer processing operation.
The thermoforming means the pressing with the heat, right?
Yeah.
The,
Where
what
do you find
I
this? Your coffee cups, tea cups. Okay, so they are thermoformed. And then your tablet strips and all. Okay, in those
okay,
places, thermoforming operation is used. Okay, so that can be done. Similar kind of operation can be done with the PBS. Okay, so these were discussed, and then what about biodegradable thermosets and elastomers? So earlier there is a lot of discussion on these thermo plastic based systems. So what about thermosets? For example, epoxy and polyurethane. Okay, so for these materials, what kind of biodegradable aspects can be brought in? So here there was a discussion on use of vegetable oil as a raw material for their manufacture. So that was discussed, and how the groups present in vegetable oil can be utilized as a biodegradable group. If you replace instead of petro based materials, if you use vegetable oils, can it be biodegradable, and can it have a similar property? So these aspects were all thought process were all discussed in this part of biodegradable thermosets and elastomers. Okay, thermosets means and elastomers both are cross-linked systems, right? So these were all discussed in this lecture. So these were the part of week 12 lectures. Now let's get on to the practice assignment session. Okay, first question. Select the origin, primary or secondary, for the given set of mesoplastics, microplastics, and nanoplastics. Okay, so the set of plastics are inks, film embrittlement, personal care products, tire abrasion, which becomes primary and which becomes secondary.
ink and personal care products are primary.
Okay,
The rest of them are secondary.
secondary. Why do you say this is primary and the other two are secondary?
Just a random guess one.
Okay,
I don't know.
okay. Yeah, you're right. Ink is primary, film embrittlement is secondary, uh, and then personal care products primary, tire abrasion secondary. So, you know, why is it primary and secondary is that because in case of these inks and personal care products, they can directly get into the effluence from the industry. Okay, whereas film embrittlement means some changes have happened. Okay, it is not the original product. Some changes have happened, and some kind of a degradation has happened to the material, and then it becomes the source of pollution. So that is why it is a secondary. Okay, in the secondary source in the environment. Okay, uh, abraded tires means it has gone through some abrasion, and all the tire is not in its original form but some abrasion. Film embrittlement means it has become the film. Films are generally flexible, right? So they have become brittle. So some modification, some changes have happened, maybe due to some plasticizer has gone out. Okay, or some other material has come in and it has caused some cross linking and it has made the material brittle. So there are some already changes that has happened to those materials. Now next, microplastics have also been identified in digestive tracts of vertebrates and invertebrates. Is it true?
True, ma'am. It's true.
Yes, it is true. So we could see the impact of plastics now. It has been identified in digestive tracts of animals and other fauna also. Because microplastics again, the macroplastics are broken down into some size, smaller size, because of some degradation that has happened. And for example, if it is in ocean and all, no, it affects the marine environment. So these microplastics, since they are of very small size, when you are, it can be in some water source. So when you drink that water, obviously you are consuming that microplastic also. Okay, so you are right. Next, reassociation of starch molecules when gelatinized starch is cooled is referred to as, is it biodegradation, or is it repolymerization, or is it retrogradation, or is it thermal degradation? What is reassociation of starch molecules when gelatinous starch is cooled?
Repolymerization.
Is it repolymerization?
Because when it is cool, it becomes solid again.
Yes, it becomes solid again. It is actually called as retrogradation. Okay, so when you dissolve starch, this you could have seen in at home also. Okay, starch powder, or people make even, yeah, starch powder is one of the common use. People would even use this, for example, rice cooking itself. Your dissolution of water, and then with heating, so the starch melts and it reorganizes or recrystallization, so the restructuring happens. This process is when it is cooled, it is called as retrogradation. There is no repolymerization that is happening, but it is just retrogradation, that is and you can see that reassociation of starch molecules, it is actually reorganization of starch molecules. Okay, that is what is happening. It's called as
Okay.
retrogradation. Okay. Next, arrange the biodegradation of polyhydroxybutyrate in the increasing order of its duration. Anaerobic biodegradation, marine degradation, bacterial degradation in tap water. Which takes the shortest time and which takes the longest time?
The longest time would be marine degradation,
Okay.
and shortest time will be bacterial degradation.
The second would be anaerobic degradation, you are saying. You are right. So bacterial degradation in tap water takes 40 days for polyhydroxybutyrate. Anaerobic degradation takes few months, and actually marine degradation takes years. Okay,
And
so
actually, what's the reason?
see, maybe in marine environment, it's salt is present, right? So that may have an effect. That is why biodegradation. When I was discussing the recap, I was saying that pH, salt, ionic strength. Okay, all these temperature, everything plays a role. Concentration of oxygen. Okay, so that may be a reason behind this. Okay,
Yeah,
so salt concentration also. So your tap water may also have some salt, but compared to a marine environment, you know, and availability of microorganism, what kind of microorganism, suitable microorganism is there? Because a particular microorganism can act on particular type of polymer or any particular type of material only. Because that microorganism will have certain kind of enzymes which are specific to certain kind of materials. So that kind of microorganism availability in marine environment may not be, possible. So the degradation may be through other aspects. Okay, it cannot be through bio based degradation and all. So there are a lot of aspects. It's not that so you have to give that every proper condition so that the biodegradation happens. Okay, so alteration in condition will affect biodegradation. Okay, so lot of aspects plays role. That is why the uh, your rate of biodegradation is very very important. The first step in aerobic degradation of polylactic acid is, what might be the first step?
Hydrolysis,
Yes. Why do you say hydrolysis?
because it is ester, polyester.
Yes, you are right.
Is
So
it correct, man?
yes, 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 it's
Mm.
correct. Though we say it as polylactic acid, it is actually lactate. Okay. So this lactate is nothing but your ester, CO group. So in aerobic degradation and in presence of water, so this water will hydrolyze the ester bonds, forming acid and alcohol. Okay, that is the first step. Okay, so you're right. Next, one of the key challenges in application of polylactic acid is,
Because
no, not the cost. Cost may be one of the
uh,
aspects, but that is not the main.
I don't know.
Something related to structure.
No idea.
Okay, it's actually controlling its stereochemistry. Okay, polylactic acid has two enantiomers, L and D. So you would have heard of this, stereoisomerism and all, right? Enantiomers. So how do they rotate the plane polarized light? This you would have come across in your 11th and 12th chemistry. So it has two enantiomers. So what is the issue with the enantiomers is that the D enantiomer, polylactic acid D, it has high crystallinity. Okay, when there is a higher crystallinity, the biodegradation is comparatively slower. Okay, so that is one of the key challenges. Okay, and processing will also be, obviously, difficult. When you have, higher crystallinity. Okay, so this is how it looks. D and L polylactic acid. Next, petroleum-based biopolymers are all non-biodegradable. Is it true or false? Sorry, petroleum-based polymers are all non-biodegradable. Is it true or false?
True.
Is it true?
Polyethylene and all are non-biodegradable.
Okay, polyethylene are all non-biodegradable. There aren't any polymers which are of petroleum origin but which are biodegradable.
No, man.
Actually false. There are polymers which are of petroleum based but they are still biodegradable. Example is polyvinyl alcohol. It is a petroleum based polymer but it is biodegradable. Why is it biodegradable? It's basically because it's a water soluble polymer. Okay, and it can be degraded because of the hydroxyl group present. Okay, if you just look into the structure, this is the structure of your polyvinyl alcohol. So you have this OH group. So this can be degraded. Okay. Uh, and because of this, molecular activity, the chain scission can happen and eventually it gets assimilated and mineralized by microorganism. Okay. So they can be broken down and then, acted upon by microorganisms and eventually biodegraded. Okay, so not all petroleum-based polymers are non-biodegradable. There are, certain category where biodegradation is possible also. Okay, next. Polyhydroxybutyrate is brittle in nature. Identify the key challenge in application of PHB based PHB based on the discussion in lecture 87 and also related to the brittle nature based on your knowledge of stress strain curves.
The challenge would be processing,
Okay.
and its strain graph would be having very steep slope.
So, okay, in one way you're right. Yes, you got it, but the terminology you didn't get. How do you say it will have stress strain graph will have steep slope? From which point did you decipher that it will have a steep slope?
Brittle nature.
Yes, good. Oh, so the brittleness of polyhydroxybutyrate, why is it a challenge? Is that why is it highly brittle? Is that there is a formation of large crystalline domains. So large crystalline domains in the form of spherulite is there in polyhydroxybutyrate, and this is the reason behind its brittleness of polyhydroxybutyrate. Okay, so due to the large crystalline domains which form spherulites, okay, the polyhydroxybutyrate is brittle. Now, the key challenge in application of polyhydroxybutyrate is toughness. Now, tell me, how will you estimate toughness and why is brittle nature related to toughness and it is a challenge here?
Brit tough. If it has less toughness, it can't handle much strain.
Yeah. So, will it have less toughness or more toughness?
Less, more toughness.
More toughness. Is it so? Actually, it will have less toughness because if you just look into the stress strain curves, generally for brittle polymers, as you said, the it's a steep line, right? That means the area under the stress strain curve is very low. So if area under the stress strain curve is very low, that means toughness is very low because toughness is nothing but energy absorption before failure, which is given by area under stress strain curve. That means polyhydroxybutyrate, because of its brittle nature, they have low toughness, which is a key challenge in its application. Okay, so brittle polymers show low toughness. So that is why polyhydroxybutyrate, which is a brittle polymer, uh, finds this difficulty in application. You are able to understand, right?
Yeah, man.
Okay, fine. And why is it brittle? It is because of large crystalline domains. Next question. Growth of microorganism can be used as a measure of biodegradation. Identify true or false. Is it true? If
True.
microorganism true. So you're saying that if microorganism is present on some polymeric material, that means biodegradation is happening in that material.
Uh, Microorganisms cause the biodegradation. Degradation.
Yes, microorganism, they play a role in biodegradation. But does the presence of microorganism uh, show that this material is being degraded,
Yes,
biodegraded,
ma'am.
biodegraded?
Yes,
Okay,
ma'am.
it actually false. A mere presence of microorganism, it is not a measure of biodegradation. For example, you can find, if you take, your polyethylene bag. Okay. Due to some water present or something, you would have taken some fruits in polyethylene bag, and that fruit would have got some moisture or something, and because of that some microorganism might be growing there. But that does not mean that polyethylene is being degraded by the microorganism. Okay. It is just that microorganism, due to some other, condition in it, is growing over there. But it does not mean that it is breaking that compound and degrading that compound. Okay. So
Okay.
weight loss or disintegration or growth of microorganisms, these are not, the actual, measure of biodegradation. Okay. So there should be, this polymer, should be used as a source of carbon by the microorganism, and they should be used in their process. Okay, then only, you can say that biodegradation is happening. Okay. Next, microplastics are also prevalent in atmosphere as aerosols. Is it true?
True.
Yes, true. Because of their size, they can also get into the, uh, you know, atmosphere and form aerosols. Okay. Next, promising factor for biodegradation is rate of degradation should be greater than rate of accumulation. Is it true or false? If rate of degradation is faster than rate of accumulation, then it is a promising biodegradation process for that particular material. Is it true?
Even it's degradable, then the polymer will not be accumulated.
Yes, I'm saying if the rate of degradation is greater than rate of accumulation, uh, is it a promising? Is it, good, that particular biodegradation process? Is it good? Is it is
Yes,
it a
ma'am.
promising factor? Yes, it's true. Uh, because, always, the rate of degradation is very important. For example, you produce tons and tons of some, biodegradable polymer. Okay, but the rate of degradation, for example, we just saw polyhydroxybutyrate in marine environment. It takes years for degradation. Okay, so that means the rate of degradation is very slow in that case. But by the time the one, gram is getting degraded, you will have 1,000 grams. So which is not a favorable aspect. So your rate of degradation, to the amount you're, throwing out, should be much higher, so that it's a welcoming aspect. Okay. Next, fragmentation of macromolecules is the first step for utilization as carbon source by microorganism. Is it true or false? So should the macromolecules be fragmented first, so that they can be utilized as a carbon source by microorganism? Is it true?
True.
Yes, you are right.
But I don't know why.
It's true because, microorganisms, because very large macromolecules cannot be used as a food source by microorganism or any other biological species. Okay. So it's very hard, for the microorganism to use it as a carbon source. For example, you cannot have, a big, say for example, you are having a very big apple. You cannot as such consume it, right? You have to break it to small pieces, and then you have to consume it, right? Or you have to bite it and break it, and then only you are able to consume. Similarly, for microorganism also, macromolecules are very big. So the larger the macromolecule, the very high the molecular weight of the macromolecule, it will be difficult for the microorganism also to use it as a food source, right? So first it has to be fragmented. Okay. So that it can be you utilize as a carbon source. So first what should happen is that there should be some chain cleavage. Okay, this can be some enzymatic process also, through some presence of certain enzymes, the chain is cleaved, and then the microorganism starts using that cleaved chain as food source, and then it starts degrading it. Or some other process can happen. For example, in lactic acid and all, polylactic acid, you said hydrolysis, so that through hydrolysis it is broken down, right, into acid and alcohol, then it can be used by microorganism. Or there can be oxidation process or some other means or combination of steps that can be used for this chain cleavage process to happen, and then microorganism starts utilizing it, okay, for the biodegradation to happen. Hope you got it right.
Yes, ma'am.
Okay, next. Toxic intermediates are acceptable in biodegradation. Is it true or false? Can we accept toxic intermediates in biodegradation?
And no, ma'am. It's false.
Yes, it's false. So, ecotoxicity of intermediate product assessment is an essential factor involved in biodegradation. So, preferable and common intermediates would be some biomass. Okay, so that can be some intermediates, and then further it breaks down and then it gets converted to energy, carbon dioxide, and water. Okay, so that is how the intermediate should be. It cannot be toxic. If it is going to be toxic, again, it's going to be a sustainability issue. Okay, so as you said, toxic intermediates are not acceptable. Next, bioassimilation and mineralization is a final step in biological degradation process. Is it true?
False.
Why do you say it is false?
Well, it will be degraded, no, ma'am. So nothing would be left.
Yes, it will be degraded.
Won't leave anything behind. So
So actually, it is true. Bioassimilation and mineralization, is the final step in biodegradation process. Bioassimilation means it is being used up, it is assimilated, okay, by the microorganism, and then converted to energy, and then some inorganics and all, no, they get mineralized. Okay, so that is the final step. So when you see a biodegradation process, what are the steps, general steps involved is that there will be involvement of enzymes. Okay, as we saw in the previous question also, there will be some enzyme involvement to break down the large macromolecule. So this process can be aided by acids and peroxides. Okay, some byproducts which are byproducts of biological pathways, and then through this the chain cleavage proceeds. So it can be also aided by hydrolysis, photo or thermo-oxidation and all. Okay, once this happens, then formation of products like the microorganism, now there's a cleaved product, right? So this can be used by the microorganism as carbon source, and then you have some oligomers, monomer derivatives and all. Okay, and finally, what further action of the microorganism, what it will lead to is they will get converted into metabolic energy, which is bioassimilated in the organism. Okay, and some inorganics get converted into they are mineralized. Okay, this is how the process happens. Okay, so bioassimilation and mineralization is a final step. Okay, and most common microorganisms that are used that are involved in this process are bacteria, fungi, algae and all. Next, macroplastics have higher surface to volume ratio than microplastics, that leads to increased interaction with environment than microplastics. Is it true or false? Does macroplastics have higher surface to volume ratio than microplastics?
true.
Sure.
The macroplastic is more exposed than microplastics.
Yeah. It's actually false. So your microplastics are more exposed. As the size reduces, the surface to volume ratio, it increases. Okay. That is why, when you one of the fundamentals of nanotechnology is that when you bring down the size, the reaction, their reactivity, their functionality and all, improves like multiple folds. So the same here goes for this plastics also. Here, for example, a 5 micro millimeter sheet, if it has a surface to volume ratio of 440 meter square per meter cube, then a 50 micrometer particle will have 1 into 10 power 5 meter square per meter cube. You could see how much the surface has increased to a particular unit volume. Okay. So as you actually reduce the size, your surface area per unit volume, it actually increases. Okay. The amount exposed. For example, 1 centimeter cube, uh, uh, of a cube will have particular surface. But if you break that into hundreds of small cubes, then each small cube will have 6 surfaces, right? Compared to one cube. One cube will have 1 centimeter cube will have 6 surfaces. Whereas if you break it down to 100, then 100 into 6 surfaces will be there. Correct? That means your surface area per unit volume has increased. Correct? Are you able to realize it? Are you able to understand?
I can explain once more.
Yeah. See, for example, if you take a particular cube, okay, a cubic structure, okay, a cubic structure, it will have 6 surfaces, right? And the volume of
Yes,
the volume of the cubic structure, you can imagine it as 1 centimeter cube. Okay. Now you're breaking that 1 centimeter cubic structure to 100 pieces. So, for example, you imagine that you're breaking into 100 equal cube pieces. You're breaking down into 100 smaller cubes. Okay. Then, how many surfaces each cube will have? So, total number of surfaces, just imagine. The same piece you're breaking down into 100 small cubes. That means your surface is getting increased, right? The exposed surface. Here
okay,
you had 6 surfaces. Here you have 6 surface for one cube, but there are 100 cubes, right? There are
okay.
600 surfaces. So each surface will have some surface area, correct?
So for the same volume, there is more surface area.
More surface area, more surface that is
Okay,
exposed. Okay,
okay.
that is what is the case. Next. Starch is composed of dash and dash. Is it composed of branched amylose 20 to 30% and linear amylopectin 70 to 80%? What is it? Linear amylose 70 to 80% and branched amylopectin 20 to 30%. Uh, hmm, Linear amylose 20 to 30% and branched amylopectin 70 to 80%. Or is it linear amylose 20 to 30% and linear amylopectin 70 to 80%? What is the composition of starch?
Option C, ma'am.
Correct. Yes. It has linear amylose of 20 to 30% and branched amylopectin of 70 to 80%. Okay. So these linear amylose, they have 1,4 alpha 1,4 linkage. Uh, Amylopectin, they are made up of glucose units. Amylopectin are also made up of glucose units. Here, the linear part of it is having 1,4 linkage and the branching is having a 1,6 alpha linkage. Okay, between the glucose units. Okay, next.
Yeah, this was there in a biochemistry subject. This
Okay,
this
okay,
topic.
good. Strength or strain at failure of polybutylene adipate terephthalate, a biodegradable polyester, is similar to dash. Is it similar to pectin, or is it similar to cellulose, or is it similar to LDPE, or none of the above?
and none of the above.
Do you think so? You don't think it may match with any of the other polymers mentioned?
I don't know.
It is very similar to LDPE. Okay. So, you can think of some application where you need that strength or strain at failure similar to LDPE. So, you can start replacing LDPE, which is a non-biodegradable polymer, to PBAT, which is a biodegradable polymer. Okay. However, there are certain other aspects also, but this service comparison of only this property, then this can be a good replacement. Okay. Now next, chitin is a biopolymer. Is it true or false?
True.
True. Yes, chitin is a biopolymer. Okay. So they have amine groups. Okay. They are present in your exoskeleton of your insects and all. Okay, it's of animal origin. So this can also be converted to another polymer called chitosan by just removing the acetyl linkage, so that you will have amine linkage alone. So you form chitosan. Okay. Next, arrange the degradation step of polylactic acid in the presence of water. So you have certain degradation steps of polylactic acid. Now you have to arrange it. Which one is the first step? Which one is the second and third and fourth step? So the steps given are hydrolysis of crystalline domain due to increased acid concentration, decrease in molar mass of amorphous domain, diffusion of water in polylactic acid, hydrolysis in amorphous domain. Which should be the first step?
Option one.
No, no, no. You have to arrange this in the correct order. It's not the option. You have to arrange these four steps in the correct order. Which is first step, which is
Will-
second step, third step, and fourth step. So degradation,
First step
mhm.
will be diffusion of water,
Okay. Next.
then hydrolysis of crystalline domain,
Okay.
then hydrolysis in amorphous domain, and decrease in molar mass.
Okay, you're saying that way. Is it easy to hydrolyze crystalline domains compared to amorphous domains?
I don't know.
The first step you said is right. First, water has to diffuse in the polylactic acid. Okay. And the next step is actually hydrolysis of the amorphous domains, because you can easily access the amorphous domains. Okay. They are not well ordered, right? So you can easily break down those amorphous domains, hydrolyze the amorphous domains. And then, so this causes decrease in molar mass of the amorphous domains, because hydrolysis is happening, ester bond is broken, and acid and alcohol is formed, right? Sorry, yeah, acid and alcohol is formed. So there are obviously there is hydrolysis, so this causes decrease in molar mass of the amorphous domain. And then, you know since there is a hydrolysis of amorphous domain, acid is being formed and the acid concentration starts increasing, and then this hydrolysis of crystalline domain starts happening. Okay. So when there's all due to the increased acid concentration. So when there is a amorphous part and crystalline part, always the crystalline part is little difficult to handle compared to your amorphous part. Okay. For example, even diffusion of molecules, it can easily diffuse in amorphous region, whereas in crystalline region, because they are well ordered packed structures, it is hard for diffusion to happen also. Okay. So water has to diffuse in through polylactic acid, right? So first, easily it can diffuse in through the amorphous layers. It starts hydrolyzing it, breaking it. So because of that, there is an increased acid concentration. This acid concentration supports in breaking down of crystalline domains and having water to get access to the crystalline domains also. Okay, you got it?
Yes, ma'am.
Okay. Next, anaerobic biodegradation of PLA is faster than aerobic degradation. Is it true or false? Does anaerobic degradation, biodegradation happens faster compared to aerobic in polylactic acid?
False.
You are right. So, anaerobic biodegradation is very slow. It takes tens of years, whereas aerobic degradation takes few months in case of polylactic acid. Okay, next. A natural process by which organic materials are decomposed by microorganisms, small insects, earthworms, and other soil inhabiting organisms to produce humus. A soil like substance is called. What is this method called? Where you use a mix of microorganisms, insects, earthworms to produce humus.
Decomposition.
Huh?
Decomposition.
You are somewhere closer. What is the method called?
No idea.
It's composting. You said decomposition, you have to say composting. That is a process. So, when you think of earthworms, this composting, with the earthworms is like very common nowadays. Okay. So, this process is called as composting. Hope you got it. So, that's all with the questions. Any other doubts? Any other doubts you have?
No other doubts, sir.
Okay. Okay. Hope this session was useful. You got some idea.
Yeah, I got some idea.
Okay. Okay. Please go through the
Yeah,
lectures
yeah. After this,
and
I'll go through the videos.
yeah, we'll just go through the lectures. And in case of any doubts, please post it in the forum. Okay. And also, just try to brush up all your lectures also, because probably next week we may be having one final session. Okay. So you can ask whatever possible doubts in that session. Okay. And also post it in the forum also. In the meantime, also you can post it. Okay, so that you can use make best use of the session. If you post it in the forum also, we'll try to answer it as soon as possible, and we can have the discussion of the same in the next session also, or you can also ask in the next session. Okay, because next session might be the probably the last session. Next session will be definitely the last session. Okay, after which you will have your exams, right?
Yes,
20th year, yeah. So please make use of the session. Okay. Yeah, just brush up your you know uh, lectures, and any doubts, please make a note of it and try to utilize the session as much as possible and the forum as much as possible. Okay. So that you can clear all your doubts before your exams. Okay.
yeah,
So
okay.
okay, if there are no other doubts, then we can officially end the session.
Yeah, yeah, sure, man. Thank you.
Okay, thank you. Happy weekend.
You too, man.
Thank you.